We're back. All right. It's been a while. Change of background also. Christmas is here. I didn't move yet. If you've been paying attention, I said I was going to move. Haven't moved yet. But I had to make room for the Christmas tree, so I moved the desk from there. Now I'm in a corner right in front of the window. I haven't posted in a while, mostly because I'm still waiting for parts. It's kind of crazy, right? So on the last video, I talked about how we're going to upgrade. First of all, we need an IMU. That was the biggest part. An IMU in order to balance our weight better, and so we can work in a straight line. I've kind of like socialized this idea with other people who know about robotics, and everyone agrees that yeah, it's probably like a good next move. So I felt good about that. But I also ordered a few other boards: a Raspberry Pi, an RP 2040. A Servo 2040, which runs on a RP 2040, to try to like clean our wiring a little bit. And all those parts are coming from Adafruit, which is this website here, Adafruit, which I made the mistake of ordering from here. It's been over a week. I still haven't received parts. Yeah, very annoying, very expensive. And on the other hand, I ordered some replacement servo horns. So remember, the other thing we were gonna change was the servo horns keep stripping. So I ordered these metal servo horns. I don't know if you can see here, right? So this guy is gonna replace. Oh, actually, I didn't notice the size difference. That could be an issue. This guy would replace this guy, right? And the main difference is, of course, that it's a metal part, especially where the teeth bind. So it's not gonna strip. And we have these for the knee horns, which the size is an issue. And we have these for the shoulder joint, right? So the shoulder joint, yeah. So instead of pressing this into the servo, we're gonna mesh this, which has metal grooves. It's gonna be impossible to see. It's gonna be impossible to see it, but it basically has teeth there. So I think this will be much better. Of course, that means we gotta redesign this part, right? Because this part basically has this metal servo feature to interface with the servo built in. We need to replace it and bring back this thing, right? Put it here, and then this has to screw with these. So more screws, but you know, it's funny because we are going back to the original design, but that's fine, just because, you know, we wanted to remove as many screws as possible, and we kind of did it, and now we're finding out that maybe we went too far, but that's fine. At least we tried, right? So so that needs to happen. So there's some CAD work that needs to happen, but I wasn't gonna get started on that anytime soon, just because it's very small stuff, and when the new boards come, if they ever come, and the new IMU comes, we still need to find somewhere to put those things in, right? So that's more CAD work. So I was gonna pile all that CAD work together. Yeah. And so actually, in the meantime, what I thought we could do was, of course, we've always said, you know, robot has to walk, right? And we're very close. We basically can walk. It's just not a clean walk. IMU will help. But the next step after that really is a machine learning controller, right? This whole idea that we want to walk like the Disney Bipedal robot, which is walks in an animated way. There's an architecture diagram here somewhere, I think. I swear there's an architecture. I thought there was an architecture. Okay, I thought there was an architecture. It's kind of like this, right? Mechanical design, done, right? It's done. Animation authoring. Okay, we haven't done that yet, but it's like, come on, how hard could that be? And these all fits into the RL, reinforcement learning. So I thought, okay, let's get started on these, right? We need a simulation model. Imitation reward, that's interesting. Train with PPO, right? So those steps, train with PPO, for example, right? Maybe perhaps we can start there. Once we know how to train any model with PPO, then maybe perhaps we can, you know, work our way here and look into simulating our own robot, because we haven't done that yet. We have it on OnShape, but to get into a gym like MuJoCo or Isaac or PyBullet, there's some work to be done, right? You have to like kind of like code all the joins and stuff. I've never done it. I've heard it's a pain. We're gonna find out. And then there's other things here like low-level design, actuator models. Actuator models will require some work. It's because we're working with Alibaba and servos, so we know very little properties of these models. But of course, if you're simulating something, simulating servos, their behavior on a gym, so on a virtual environment, you need to know their properties. You need to know how fast they can move, how much torque. I don't know what else you need to know, but I'm sure there's things. I'm sure there's things you need to know. And low-level control. I was Googling a little bit about these. It's basically, how are you going to connect your ML model to the servos, right? So right now servos are ruled by Arduino, right? But an Arduino cannot host a ML model. A Raspberry Pi 5 with an AI hat, which is what I've ordered, can. So now these two need to communicate. This is pretty straightforward, actually. There's like you basically upload some code for your Arduino to act like a receiver over serial comms, and then any computer can run Python or MicroPython, like on a Raspberry Pi on a RP 2040, and send commands via that. So that's one way of doing it. I'm sure there's other ways. I'm sure maybe like everything feeds on the Raspberry Pi, and we can just connect all the servos there. But that's pretty straightforward. What I don't think it's straightforward is the training models, right? Like that part, I've never done before. So I thought we would spend some time today, maybe tomorrow too, doing it. So I have a list of things here I want to kind of do. I might have done some tutorials in the past, but I think that code is out of date now. So I've kind of like wrote some things here in order. That we can take, and I think it will be a good learning experience. One thing I would say is that I've noticed there's very little tutorials on RL. Anything reinforcement learning, if you want to run how to teach a robot how to walk, if you go on YouTube and type that, basically nothing comes out. Like there's some short videos showing like, oh look, the robot's walking. There's no like hand-holding tutorial showing you step by step. I don't know why that is, right? Because we have hand-holding tutorials for like, oh, build your own LLM from scratch, right? But the same doesn't exist for robotics for some reason. The good thing is we do live in the LLM era, so we can just ask ChatGPT to help us. But I just thought it's interesting. Perhaps someone should do that. Okay, last thing I want to mention here was that there's this upcoming hackathon by K-Scale. It's on December 14th. It's in Atherton, California. So it's in the Bay Area. It's basically a Palo Alto area, Stanford area. But if you're from the Bay Area, you can still attend remotely. It's fine. But I wanted to point out one thing here. The price, third place gets a 3D-printed Seroth. So a Seroth is this little humanoid robot. It's pretty cool. These are like $300. I would take that. Second place, prototype production ready Seroth. So like another Seroth, but it's metal. It's not 3D printed. Could be nice. And the first place gets a full-scale K-scale robot. So that's a humanoid robot, right? So let's see if I can get a picture. Where is? Okay. Well, there are no pictures. That's odd. Maybe under Twitter. Anyways, it's a big robot, all right? Like having that, if you actually win that would be pretty cool. Okay, somehow there's no pictures of it, but it's big. I've seen it in person. It's big, trust. Like this is what it looks like. Of course, this is a 3D printed version. The thing is, it's metal. It's huge. It's big. So it'll be pretty cool to win that. So just for that reason alone, you should attend this thing. Yeah. I'll put the link here on this document. Really cool hackathon you should attend. By the way, this document's link is in bio. You can just go and jump in there. Anyways, so let's get to coding. So the first thing is to install OpenAI Gym. It's not the OpenAI Gym anymore, actually. So it used to be by OpenAI, but it's now called Gymnasium, and I think it's Gymnasium. It's open source. So they fork it, and now it's run by Farama. I don't know what Farama is actually. The Farama Foundation. Anyways, this is Gymnasium. Let me put it. It's basically like this virtual space. Okay, Farama Foundation just maintains open source repos, so it's just an open source repo now, Gymnasium. Anyways, Gymnasium is like this kind of like, this is all new to me, by the way. This is my understanding of Gymnasium, is that it's like this like virtual environment where you can test different things. So they have already some predefined environments, they call them. For example, on this one here, on this GIF, they're trying to land this lunar lander between these flags, you know. And so it's almost like games, right? It's almost like games you can execute on code, and you can use these games, or you can train models to basically beat these games. And what's special about these games is they're not just games, right? So they're games, but they also have reward functions already established. And so what a reward function is, it basically tells your model how well it's doing, right? So imagine if you were trying to land this lander here. If you fail to land it or crash it, you know, you should get a penalty, a negative reward. So your model knows, hey, you did that wrong. So these things are already built into this environment. So that's cool. And of course, the reward functions are a little more nuanced than just that. You know, for example, I think the lander has like, you know, every time you like push a thruster, you know, you spend some fuel. So that's a negative reward. So you have to like watch your moves and things like that. But anyways, there's a bunch of, if you go see here under environments, there's a bunch of environments here, very classical card pull. You know, if you ever took a controls theory class in college, you know these, right? These are usually solved with PIDs. But here you can do it with an RL model. It's like, yeah. And then you have Box CD. You have a bipedal walker, which is very relevant to us. They have a car racing environment. I actually have never seen that one. That's cool. And then when you go to toy text, I haven't seen a lot of these. But when you go to MuJoCo here, this is when it gets 3D, right? So MuJoCo also open source 3D sim. You know, it basically has good physics. MuJoCo is like same as Isaac Lab, if you know Isaac, or Pybullet. These are all like the same thing basically. Like not exactly the same thing, right? Isaac is owned by NVIDIA, and also, but I mean, like the functionality is very similar. You can run models in 3D in a 3D environment with good physics. And I'm sure one of them has better physics than other, but on my basic understanding, they're very similar. So you can see here, you see ant model. So they define their action space, observation space. We're going to talk about what all of this means. Observation space is basically the data that's available for your model to learn from, and there's a lot of stuff here. The reward function, like I mentioned, you know, how is the model rewarded and for what. So the documentation is pretty good, and the predefined environments are pretty good. There's even a humanoid here. Yeah, so you can train a thing to walk, I guess. Double pendulum. So a lot of cool things here. And there's an Atari thing here. Atari documentation. Okay. I don't know why Atari is here. I guess you could actually also connect it to Atari games. There seem to be some tutorials here. I haven't seen any of these. But anyways, that's Gymnasium. And probably not gonna read tutorials. Probably just gonna go for it. Yeah, so yeah, so let's see what we have here. Okay, make dear. I'm gonna call these RL learn, and I'm creating this in the GitHub repo so everyone has access to it. The other big change I've made recently is I was previously using VS Code with the double extension. Right now I'm trying Cursor. It's actually a very similar product, but I don't know. I'm happy with it. So check out Cursor, I guess. I feel like everyone already knows Cursor. Anyways, I did have my little plan here. Let's try to stick to it. Let's try to have some order. So install Gymnasium. So let's do that. Let's show what Gymnasium is, right? And sorry, I'm just reading some notes here on the side, but all right. So we're gonna start. Oh, should have kept the docs open. Let's skip. Okay, let's use these docs. So let's start with a very basic example. Classic controls. Cart pull, for example, right? Cart pull, right? So so let's use this environment. It's cart pull v1, right? So we bring this here. I'm gonna create a folder called cart pull, and then I'm gonna cart pull by, right? So Gymnasium is not defined. Yeah. Okay. So by the way, this is cursor chat feature. Should look like the same as double. Should be no change there. I think I'm gonna change my thing to light thing. I know it's kind of weird, but oh, I just have a window behind me, so this room, there's a lot of light on my eyes right now. It's like having a dark one feels kind of weird. Anyways, yeah, so we gotta let's figure out the bare minimum to make this work. All right, so we're gonna import Gymnasium. Obviously, autocomplete was suggesting things here. Looks like autocomplete is suggesting this structure. Okay. And then I think if you want to see it, you need to set the render mode to human, right? So if you don't set the render mode to human, it'll run, but you won't be able to see it, which is normally good because, you know, if you're running a lot of simulations, you don't necessarily need to see them. You're wasting resources in rendering these things. So let's go cd cart pull and Python cart pull py. All right, nothing happened. This is interesting. True. Let's try this. Interesting. It's suggesting some code that would essentially kind of like train the model, except there's nothing to train. We haven't defined anything. Okay, a window open here. All right, cool. So this is our environment. I don't know what it's basically not doing anything here. So I'm gonna kill these here, and I'm gonna say let's feed random inputs into our environment. Let's see what it proposes. Just to send some random actions here. Observation info reset. Okay, so this is just initializing the environment. Terminate false. Okay, so this will make sense because you should know that. Well, I mean, okay, when you run the environment and you do a step, so a step is, I think it's an interaction with the environment. So your model is interacting with this environment. The environment returns all these variables. It returns 5 things: observation, reward, terminated, truncated, info. This is on the latest version of Gymnasium. Before it used to only return 4. So terminated and truncated used to be together in one variable called done. It essentially does the same thing. It's just terminated and truncated basically break down different. It's the same thing, like the environment got terminated, but for different reasons, and terminated and truncated distinguish these reasons. I honestly haven't used it either or. And here you can see action, environment, action sample, action space sample. So this basically creates a random action. And so if we try running this again, you should be random actions, right? Okay, so one thing I want to change here is basically, you know, every time it gets terminated, it's turning off the simulation, so we're not seeing it fail. And I actually don't know what constitutes like termination for these. We can check the docs, but card pull, you know, so this time around, I know what's the issue. We keep resetting here. Let's just check this out. I just want to show you, I just want to show that we can make it fail. I want to see it fail. Let's see. All right, should be able to, okay, great. There, right? It failed, it didn't reset. And now it went, who knows where it went. But yeah, okay, so first of all, let's pull out the docs here for the card and let's see observation space. Reward episode end, right? So termination, if the pole angle is greater than 12 degrees plus minus, so either direction, it gets terminated. If the card position is greater than 2.4, so if it goes off display, it gets terminated. And if the episode length is greater than 500 steps, I imagine, right? So there's more than 500 terminations, it gets terminated. So that makes sense. That's why it was getting terminated before, because so if we go back to these, it was getting terminated because the angle, you just take a, what? Oh, sorry, my bad. It was getting terminated because of the angle was more than 12 degrees, I guess. And we don't have to guess, actually. We can know this by printing the observation, right? So let's see what the observation prints, actually. Let's print the observation. All right, so we're printing the observation. We're seeing these. I don't know what is this, like an array. And there's 4 values here, right? So we go back to the docs here, observation space. You see the 4 values. So one is card position, card velocity, pole angle, pole angular velocity. The pole angle gets reported in rad. Apparently 0.4 rad is equals 24 degrees. The termination is pole angle at 12. So 0.4 divided by 2, it's like around 0.2 rad. So we should be seeing on the 3rd value around 0.2 rad before it gets terminated, which seems about right. Yeah. Actually, let's make it even more clear. I want to fully convince myself that what I'm saying is correct. Terminated. Okay, this will make way more sense. Okay, yep, terminated. Well, terminated. All right, we have a few terminations here. Terminated here, you know, the angle here over 0.2 rad, over 0.2 rad. All right, now I'm convinced. Are you convinced? I'm convinced. Cool. All right. Anyway, so that's what Gymnasium is. And yeah, we had carpool here, but there's a bunch of things you can do, right? So another one here would be this one here. And yeah, you can all you have to do is change them like that. I'm not familiar with this one. I imagine what you want to do is rock and go to the flag. I don't know. Never used that one. But yeah, let's stick to stick to carpool here. Anyways, now that we have these, the next question would be, okay, how do we solve these? Wait, is that the next question actually? All right, done. I'm gonna tick that one done. Oh, and I'm gonna try to match the YouTube video time episodes to these, because it's always a pain to go back through hours of video and be like, oh, this is where this happened and so on. Anyways, next step is to solve. Let's train a model to keep our card pole in the air. Let's see how long it can keep it in the air. And let's do that. And there's two ways of doing it. So there's this library called SV3. I forget what it's stable baseline 3. So I think this is the easiest way to implement an RL kind of like pipeline, like train an RL model right now in this day and age. And it's very cool. It's Python and open source and supports a bunch of RL algorithms. I don't have a lot of experience with all of this. I would actually just in this video I would want to try all of them and see which one performs better. Try different algos other than PPO. PPO, I've read some papers. Well, the Disney paper references PPO, so that's why I was like, oh, let's try PPO. But we should try others as well. But before we use these, there's also this thing called the NEAT algorithm. NEAT Python. Neural evolution of augmenting topologies. And the reason why NEAT is cool is because you don't have to predefine any parameters, number of layers, neurons, connections. It basically does it for you, right? So if you are facing a problem for the first time and you don't know what kind of model you need, what kind of network you need to solve it, NEAT basically iterates through different network architectures and figures out which one's performing best. There is some videos that could explain this better. And really, yeah, there's the NEAT algorithm is NEAT introduction. I watched both very good. Anyways, the reason why, yeah, like I've heard NEAT is one of the easiest ways to get started. So let's do NEAT, right? So, okay, wait, actually, let me check some notes here. NEAT Python GitHub. Let's see if there's a GitHub repo. Yes, this is it. This isn't it. Code reclaimers. This is the NEAT. Yeah, and there's some examples here, right? So this is single pole balancing, right? So they've already done what we're doing here. So we're going to implement our own version of it. Right, so let's see. This script in this section show how to solve a network that balances a pole on top of a removable card, which basically describes our environment exactly. There's a significant amount of duplication between the scripts, and then this is intentional. Okay, running. Evolve feed forward when it completes. Okay. All right. So let's start at evolve feed forward, I guess. Evolve. So you're gonna need that one. Oh. Okay. So evolve. So some people call it training, they call it evolve, I guess. So I'm gonna pull all the feed forward files. I'm gonna replicate this, right? So we need an evolve feed forward, a test feed forward, and a config feed forward. So let's add evolve feed forward.py, config feed forward. And oh, sorry, did I? Oh yeah. Oh, no, that wasn't a py. Test feed forward.py. Yes, test feed forward is not a. All right. So we could go ahead and copy and paste the config here. well, we got to start with evolve. Evolve, if we're saying this is training, we can start here. Right, so first you train your model, right? You evolve it in this case, and then you test it. You evaluate the results you tested, right? So, and so right off the bat, you can see here we have some issues here. Import carpal doesn't exist, of course, because we're using the Gymnasium. So these guys don't import Gymnasium. I don't know what, I guess they're using something else. They do import Neat, they import Visualize. Honestly, all these Visualize stuff, we probably do not want. I guess I should comment it out before deleting. Yeah. Can you read? I wonder if you can read. Or is it the letters? Is the font too small? I mean, now you can read it, right? For sure. Maybe the font was too small before. All right, so Visualize don't need, carpal no. We're gonna put in Gymnasium instead. No reference here. Runs per net, simulation set use. Okay. Carpal. Yeah. Okay. Gymnasium, yes. I think we're gonna have NumPy. Actually, I'll come later. Simulations per second. I don't think we need that. Runs per net. Like the reason why I don't think simulations per second is relevant is because, like in our previous example, the environment is going to terminate itself, right? Either it will fail or, you know, there's a maximum of 500 steps. So we don't need simulation seconds here. It's irrelevant. We have run per net. Yeah, I guess we can use that. We can leave that where it is. What else? Fitness. So we obviously do need to change all this stuff here. In range runs per net, yes. So sim, I don't know, I'm not familiar with what they were using, right? But instead of sim, I think what we want is, yes, Gymnasium. And then we don't have to set the render mode to human. We'll just wait. I think this one's pretty fast. And then our observation and info, we can initialize the environment that way. I don't know what info is. I think we don't need info. Right, so okay, delete that. Run the game simulation for up to num steps. Okay, so while simulation is under simulation time is under, okay, interesting, that's how they were doing it. Okay, so we can do it the way we were doing before, right? While not terminated or truncated, right? So we can literally just do that. Trying to like trying to figure out code while explaining how I'm figuring it out. It's interesting. It's good exercise. I feel like this is how you learn. That's what I'm doing it. Hopefully it's coming out across not too bad. We have action. Oh, we're doing this with, okay, so okay, so that was the autocomplete suggestion. Yeah, so I'm not super familiar with what fitness means here, but I think fitness for neat is similar to what a reward would be. It starts at 0. fitness equals SimT, right? That's kind of like a reward because SimT is basically how much time the simulation has spent without collapsing. So I think that's a reward function in this case. So we would want to keep that. Reward, right? Because we get reward from here. So yeah. All right, so we have that. Action. Digging. Did I miss something? Do I need that? Just okay. So I guess in theory this would train. I guess we need a better action. Let's ask for help, DA. I am looking to get a predictive next action instead of my current random action in line. How do I do this with need? Let's see what it says. Basically, I think what's missing here is we need an actual action. First, evolve it forward by update the evaluation loop to use the neural network. After training completes, you have a... Okay, let's see. Terminated false. I guess it's part of initializing it. So yes to these. Output net. Action. Okay, action. Convert output to action. Wait, okay, so that's how we get a prediction for the next step. Action 1, if output equals 0, else. If output is more than 0, else. Okay. That makes sense. Okay. I think there's some things we need to change on the here on the config. So I'm just checking notes here. But forget of the linting errors. It's because I first saved these as a Python file, but it's not a Python file. Fitness criterion max, right? So threshold. So these things basically change. The fitness criterion, like I said, we said fitness is basically like a reward. So we're looking for a max reward of 60 before we terminate training. And a population size to 50. Population size just means how many processes are going to run at once, right? So this basically depends on how much compute you have. I'm going to run this on my MacBook Air. So just to give you an idea of how much compute I have, it's not much. Reset on extension 0, not sure what that means. Number of inputs. So this is what I thought we had to change. Number of inputs, number of outputs, number of inputs, right? So if we go back to the carpal, action space, the action is ND array with shape 1, comma, which can take values 0 and 1. So I think that means according to my action space, should I be changing the num outputs, num inputs? I'm gonna link this. Yeah, I think basically the number of outputs is 2. There's 2 possible outputs. Yeah, 2. Yeah, you can only have correct. Yeah, so we have 4 inputs, right? So that's our observation space, 4. But for our action space is 2. It's 0 or 1. This could be in a this could be a single output, but the way it takes it, it's structured as 2 different values. For number of, you can have 1, but they should be changed to 2 since the action space is discrete 2. Yeah, between 0 and 1. Here's yes. Whoa. Should I change num hidden? Actually, I don't know. The num hidden. There's so many parameters when it comes to RL stuff. You can actually use by need. Need starts with a minimal network. I don't know how you can safely remove the sign. Oh. Okay. I think we can evolve this. So we hit the best fitness. We hit our fitness threshold from the first. So let's increase this to like 200. We also hit that from the start. Let's make this even harder. Instead of max, let's do mean. The mean. Okay. First of all, look how fast these generations are happening on my M2. Oh. Apparently, we have it already. That was really fast. Anyways, let's test this. Yeah, I trained before even completing my code. I don't need all this stuff. I don't need these. Don't need that. Don't need that. I don't know what pickle is. Gonna keep it next time we're using it. Okay, that's how we're loading feed winner feed forward. Loading config files, rename. Here we are initializing our environment, which we still need to do. We can get it from. We can just copy this, close this. Here, initial, and replace everything that says sim basically. Net environment, Gymnasium carpool. I guess render mode here needs to be human so we can actually see it, and initialize the environment. And then here, this is the thing, right? So basically here, right? Yeah, so first we get the action, what the model suggests we do. Then we run it. And then we render it. I don't know if we need render. We'll test it out. And yeah, I think that's it. We can ask the AI here too. Can you translate these readings to match the observation space using Gymnasium? And let's give it the this documentation. This should be straightforward, right? So sure, let's still print all the same stuff, but you gotta use the Gymnasium. Yeah, see, pretty straightforward. They're all in our observation space already, which is the numbers that the sim returns once we run one step. So now we can see what we actually test there, right? So terminator is not defined. Maybe I need to initialize these variables. Let's see. All right. It's not falling, right? It's not falling. So why don't we print our action also? All right, so 0, 1, 0, 1, 0, 1. I mean, that seems to work pretty well. What is the number of outputs to? Zero or one, can't 0 or 1 be held in a equal variable? This is nothing to do with the results. I didn't fully grasp why we have two number of outputs. See, now it's saying we only need number of outputs 1, which I know it's wrong. Let's print the output also. Okay, I see. So basically the output is two numbers, right? And depending on which number and if the output 1, so if the first number is greater than 0.5, we output 0. Oh, we output 1 if the first number is greater than 0.1, and if we output 1, the card goes to the right. And if the second number is that, we output 0. I wonder why can't we train, just experiment time, right? Just for my own sake. Why can't we have number of outputs 1? And let's evolve this way. I feel like that should work. All right. The generations. Running. Okay, well, something has gone terribly wrong already. Like, this is okay. There we go. I was gonna say something must have gone wrong because like it keeps running. Okay, and then run the same thing, just as good. One number, it works. Is there a reason? Let me see this. This works. This works. Cool. Anyway, so I was very fast, right? That's how neat. I'm gonna grab more coffee. So give me 1 sec. All right. So we train a model to balance a pole, and it's great at it, and we did this way faster than I could have figured out a PID loop to do the exact same thing. And I do feel like my whole control theory class in college was a lie. I should just have been taught these, but let's try something harder. Let's try. I'm gonna make a note here. These when my outputs was 2, but in outputs 1 works just fine. Okay, why don't we try something harder? Let's pick a different problem. Let's go to bipedal walking, right? Which is closer to what we do here, right? We're training a quadruped robot. Bipedal walk, it's just like half a quadruped robot, and it's in 2D, so it should be a good challenge, but it should be manageable challenge. I'm gonna make a folder here called neat, just so everything is kept neat. Get it? No, just so we know what solved what. I mean, it's obvious from looking at the code, but anyways, new folder, bipedal. Let's go there, bipedal, and same thing, new folder, neat. We're gonna attempt this with neat first. And we're gonna set up the same structure as before. So config feed forward, evolve feed forward. I hope I didn't make it look too easy, because I am very aware that there's a lot of things and parameters that I could be optimized and I just completely ignored. I'm not claiming here that, oh, RL is so easy. I just thought, you know, it's easy to get something very simple going. It's easier than I thought. I'm just gonna copy and paste everything we had from before, just so I don't have to be jumping back and forth to reference it. And now I can just close the everything, all the old files and stuff. Yes, save it. Okay. Yeah. So I mean, well, the first thing is our environment here, bipedal. I guess let's also initialize the environment on its own, just so we can see what it looks like. I'm gonna copy these from the carpal and bipedal walker v3. Yeah, let's run this. Okay, so this is what it looks like. These are random actions, by the way, right? So that's why it's falling. Actually, it doesn't do terribly wrong. And we're printing the observation space, right? So if we take a look here, the observation space, bunch of numbers here, got a matrix of stuff. 4 by 1, 2, 3, 4, 5, 6, right? So 24 values. And of course, we can go to the documentation, observation space. Okay, I wish I could actually write it out, but it's whole angle, angular speed. Okay. Yeah, okay. So the actions are motor speeds values in the 1 to 2 range for each of the 4 joints at both hip and knees. I just think like that is such a poor description. Like, I guess it doesn't matter, but which one? Which like what's the order? Which one's hip? Which one's knee? Which one's left? Which one's right? Rewards are given for moving forward, totaling 300 points up to the far end. If the road falls, it gets minus 100. Applying motor torque costs a small amount of points. Okay. Start point left to full horizontal. Okay. I will point out the part of the observation space here. We have, let's see, angular velocity, whole angle speed, angular velocity, horizontal speeds, vertical speeds, positions of joints, and right. So whole angle speed, whole angular velocity, horizontal speed, vertical speed. These are things we could get from an IM view. position of joints and joint angular speeds. You know, servos will give you position joints, not angular speeds. These are like basically BLDCs with proper controllers. Legs contact with the ground, so some sort of sensor ground contact. We don't have that like on our actual dog. And 10 LiDAR rangefinder measurements. Of course, we don't have LiDAR, so there are no coordinates in this state vector. All right. Okay. Well, anyways, we saw what it looks like. Yeah. So now let's grab these. Let's evolve it. Let's go here. Let's go here. Someone's smashed in my wall. I don't know what's going on. Okay, so everything. The only thing I've changed so far is the environment here. Gonna delete these. Don't need that anymore. Okay. Yes, return mean and fitness. The jump fitness is its worst performance because it runs. The genome's fitness. Okay. For this to make sense, just look at any videos that explains how the NEAT algorithm works. I don't want to spend too much time on it because the way I understand it, NEAT is not. It's very limited. Like it's not a serious algorithm. I don't know exactly why. I haven't looked exactly why, but like I said, I read some papers. They all reference PPO, so I think that's kind of like where we want to get started. But it's probably good to understand, you know, how NEAT works. It's like a pretty proven idea. I think it's been out since like 2002 or something like that. Yeah, the config file probably needs to be tuned, tweaked somehow, right? So number of inputs, first of all, number of inputs is our observation space, right? So you know, they couldn't, I think it looks like there's 24 here, but I'm just gonna give this to the AI. How should we tweak our config file based on the environment parameters? So number of inputs is like 24. Number of outputs, I think it's 4, because there's 4 actuators, and our action is torque. It wants to increase the fitness threshold. Oh, it wants to increase the fitness threshold because to solve it, you need to get 300 points in. Oh, that's a good idea, actually. I totally missed that part. 24 and 4, just like we predicted. So let's start there. I think that's basically it. That's action. Wait, actually, let me. So I guess maybe we need to change this part here. What does the output look like, right? What does it want the action to look like? -1 to 1 range. So what's the range of our current output? And I think we go to the config here. Let me ask, what is the value range of the actions? Or output. Action or output, I think it's the same thing, basically. Based on the config number for outputs, their absolute value range will be determined by the activation function. Activation. Okay. Okay, so because of the sigmoid here, it's between 0 and 1. We need to be -1 to 1. Let's search the docs for activation. Sorry, was it activation function? Yes. Activation function. Okay, built-in activation functions. Apps. Oh, I guess clamped would work. 1 to -1. That's too much. Yeah. Oh, I mean 10H would also work. Sounds like either clamp or 10H activation functions would serve the -1 to 1 range. How to pick between them, right? What's the difference? I don't understand. Like, sure, I understand the curve is different, but what is the actual performance difference? Here's a compilation. Outputs valued in 1, 2 in a smooth, better for learning subtle differences. Clamp, hard cutoff, simple computation. Okay. Okay, interesting. Sounds like we could do. Oh. Okay, why don't we run both and see what happens? Sounds like both work. All right, and so we can just take that action straight up. No need to run it through anything. And I think that would work, basically. And then we can just, let's run some generations. And like I said, I'm running this on a Mac. And I do wonder sometimes if I'm pushing it. And so let's take a look. So these are my cores are 100, all of them. The camera is lagging. The camera is so that's how we know it's real. Okay, so we just finished the first generation. Best fitness -94. All right, so let's actually let's pause here. Runs per net. Let's decrease the runs per net to 2. Let's make this a little easier. Population size. Decrease population size. Let's make this a little easier on our hardware. Alright, best fitness -6, -83, -57. I'm looking at this value here. It should be going up. Not really going up right now. Okay. Best fitness is positive now, 58. -20. This keeps running. We got a 42 there, 13. I think we said we need 300. Yeah, 300. Mean, not maximum. That might take a while. Let me restart. Let's do max here, 300. And let's increase the population size. Why not? 5, and then let's bring this to 4, so 25 each. Okay. And maybe I'll give it some time. Time to make more coffee. I'm gonna pause these. I'll be back in like, I don't know, 5 minutes.
A few moments later.
All right, so quick follow up here. We're in 22 generations in. The best fitness is -47, and we're lagging hard. Actually, camera is not even refreshing. Let me cancel. Yeah, camera wasn't even refreshing. So something is not working here. And so I'm gonna change some things up here. So gonna change from clamp to 10H. Gonna hold on, let me see. Gonna change the fitness criterion down to 200. Increase the population size and decrease the runs per net. And then we're gonna start trying again. This shouldn't take that long. Like, this shouldn't take, yeah, I think, 5-minute stops. All right, I'll be back in 5-minute stops. Look at those CPUs getting hot. I'll be back.
Eventually.
All right, so this took so long that I went and grabbed lunch, and now we're back. And I did change a couple things before leaving. Let me walk you through it. But first of all, it completed on 93 generations. On the 93th, we had our fitness score, our max fitness score, because we changed it past 200, which isn't great because it's supposed to be 300 to win this game, but it was taking too long. So what I changed was, first of all, change the activation function from 10H to clamped, just because the LLM said, ChatGPT said that clamp was more computational efficient, and we were really struggling here. And I also increased the number of hidden num hidden here from 1 to 2. The way I understand it, this basically tells the need model how many layers. I think actually, is it layers? Hold on, let's see. Number of hidden nodes that we present in initial. So how many nodes are in the initial neural network topology, right? So we already know that the model is struggling, so it's probably gonna be a bigger net. So okay, let's start with more nodes. That was my reasoning, and so anyways, it seems to have solved. It doesn't tell you how long it took, but 93, and the average length was 15.2 seconds. So basically, it took 23 minutes to solve. Now that we have that, let's actually see what this looks like. So let's go to the train. To the test, sorry. Let's go to the test. We do need to change these to correct environment. Just let me quickly read these to make sure everything's good. Another thing I learned was that another thing I checked for was I was a bit paranoid that I messed up the action, and that was why it wasn't learning as fast, but it seems to be fine. All right, so let's just evaluate this visually here. This is how we walk. I mean, I guess it's technically walking, and it's moving forward. Basically only moves one leg. See, the way I would go about this, I would reward for keeping the bodies straight. But yeah, this is what we have after 23 minutes of training with NEAT. And yeah. Now, let's try to do a better job at these, right? Let's actually let me close this. Let's actually try to this is done. Need solver for bipedal walker. It's also done. And now we're gonna do we're gonna implement a PPO model using SB3, and we can compare the results. I think just visually. But before we go there, I want to show you one thing, which I forgot to mention earlier. Wait, I guess my other earlier I was supposed to rant how these new servo horns. I got these from AliExpress. I think I paid $2, $5 for this entire bag. Gets delivered in like 4 days from China all the way to California. Meanwhile, Adafruit, I paid hundreds of dollars. They can't ship me, like a small box from New York to California. It takes them more than a week. It's ridiculous. Like, I'm all for, you know, Team America. I'm not American, but I would like to be, and you know, I think America #1. But like, come on, guys, like, we need to do better than that. Anyways, like, what I wanted to show was where is it? Here, this video here. I'm gonna put this on our document here. Really cool animatronics face. But basically, this is the coolest animatronics. Look at this. This thing looks real. It's crazy. Totally recommend following this guy. Oh, actually, I'm not subscribed. I just subscribed. Really cool stuff, but really the silicon face, he did a great job here. I think it really feels real. And so, yeah, look at that, right? And so this just makes me think, you know, in our current day and age, so many people use character AI. Supposedly people are having relationships with LLMs. Imagine if the LLM actually had this face. Imagine what people would do, right? People would lose it. If text on a screen can make us feel things, imagine what this thing that looks real could make us feel. Yeah, I think, yeah, we can definitely build a stronger relationship with these than with animals. Probably than with a dog, I would argue. I think that's still a controversial opinion, but this is it. This is happening. This is very exciting. This is what I want to spend the rest of my life on. So that's cool. Anyways, there's this library called SB3, which we saw the docs earlier for. It's here. It's stable baseline 3, and I like it because it has all these RL algorithms, including PPO, which is what Disney references in their paper. And actually, I think they tell you what algorithms to use for what. Who's gonna tell you that? Let me see. I thought they mentioned it somewhere. Maybe it's here. Third-party tutorials. No, not really. Where was this? I mean, it doesn't matter. I'm gonna try it all anyways. But yeah, okay, here we go. I mean, not really. What are all Algos to use for Bipedal? Yeah, PPO SB3. I'm looking for a table. I've seen these before. Okay, I'm not sure. Somewhere there's like a document somewhere where they tell you which ones are good for what. But anyways, doesn't matter. All right, let's go back here. No, not here. Here. And no, not that. Okay. Just fighting with my own computer. Let's talk to the AI here. So previously, we solved this with neat. Now we're gonna do SB3. I'm gonna name this SB3 instead of PPO or something, because SB3 can work with a lot of different models. So let's call this main pi. Bipedal pi. Bipedal SB3 pi. All right. Let's start a conversation with the AI, and let's say I want to use SB3 and the environment shown in. Hold on, didn't we set up an environment for the bipedal here on Nick carpal? Did we not? Oh, it's here. And bipedal pi to be able to be able to train different models. Sorry, my phone is going off. Oh, BRB. All right, I'm back. Sounds like my girlfriend has been in a car crash or witnessed a car crash, and she's helping out. Anyways, like she's fine. Someone else has been in a car crash. She's helping. I want to use the SB3 and the environment shown in bipedal pi to be able to train different models to solve the environment, to walk the bipedal robot. I want to be able to easily alternate between PPO, A2C, SAC, and the other SB3 models that might be relevant. I also want to save the best model of each training run and relevant logs and be able to visualize them in TensorBoard. I think it's called Tensor. I'm a bit rusty. TensorBoard, yes. Yeah, what else do we want? Yeah, I think that's it. I want to be able to evaluate the best models. I want to be able to pick one of the best models trained and evaluate it in a way that it renders the environment render mode equals human. And I'm gonna also pass sorry, no. What are we doing here? Bipedal walker. I'm gonna pass these. All right. Let's see what happens here. I will help you create a script that uses still to train different models. Here's bipedal SB3. Okay. Seems to be doing a good job. Script easily switching between automatic logging over the name. I already have these. Run the script. All right, let's try. Let's see this. Let's read into it. All right. OS. Okay. FPO TD3. Not familiar, but okay. These are all models, right? These are all different algorithms that we can call. PPO talked about plenty. A2C, SAC, TD3. It's probably worth reading into every single one of them how it works. The other thing that's huge here is the MLP policy. We're using MLP policy on all of them, but this basically dictates the shape of your network. That's my understanding. An MLP policy is basically what people use for robotics, but it's one of those things, one of the bigger things you can tweak. That's my understanding. All right, dictionary of available algorithms. This looks good. Oh, sorry. Create the bipedal environment. Render mode, our render mode. This makes sense. And return environment. Train. Algo name. PPO. Wait. Train. Algo name. PPO. Oh, okay, so it's PPO by default if you don't specify anything. Total time steps. Total time steps 1. Okay, create log directory. Yeah. Create and wrap the environment. Yes, make, okay. Create and evaluate environment. Yeah, eval frequency. So we're saving every 10,000. We do a callback and we save the logs and stuff every 10,000 steps. Checkpoint callback. What is a checkpoint? What is the difference between eval callback and checkpoint callback? Okay, MLP verbose, yes. Eval callback. Process training runs several evaluation episodes. If the average reward is better than the previous, saves the model. Cool. Logs. Okay, cool. So that's the eval callback. Okay, checkpoint simply saves the current model state. It creates numbered checkpoints. Best resuming training if it gets interrupted. Okay. Evaluate model. We probably don't need the checkpoint callback, to be honest, but evaluate. Okay. Okay, the code looks good, but I would like to be able to specify the algo name when executing the file. For example, I should be able to say bipedal sp3 pi /PPO to select PPO. I'm also gonna take the evaluate code into a separate file, I think. Yeah, AG parse. Yeah, exactly. Yeah, that's it. Yep, perfect. Okay, great. Now I want to take the evaluate code and set it up on its own file. Bipedal sp3. I'm going to call it. I like that it comes up with its own name because I didn't want to. Cool. Great. Now going back to the training sequence, are we defining all of the relevant parameters? For example, after how many steps does the weights get updated? I'm just surprised. It is very parameter light. We don't have a separate config file. Okay. Let me update this. There's a lot of stuff that that could be tweaked and we weren't tweaking. That I'm probably not going to tweak, to be honest. But let's make sure TensorBoard is here. It is here. Okay. Looks like it deleted some stuff for some reason. I feel like the AI does this from time to time. Well, the intro caught it. What else? When does training stop? Sometimes some people run training forever and they just visually check when the reward gets to some point and then terminate it themselves. Oh, I guess we have a determined number of steps. What is the number of steps? I know it's 1 million. I've already seen it, but okay, yeah, total time steps 1 million. Our maximum of 1600 steps per episode ends earlier if the road falls or reaches the end. A successful episode typically takes. Okay, you don't know that. You don't know that. Evaluation frequency at 10,000. Total time steps 1 million. This means 1 million steps run approximately. Okay, we will let the model every. Yeah, we save checkpoints. Where does it say that the maximum of steps per episode is 1600? I think this might be from the environment itself. That's what I'm asking. But yep. Okay, cool. That's good. Okay. The one thing is that instead of 1 million episodes here, I want to do. Oh man, is that it? Is that really it? Train model. Arcs. Let's set the default to wait, where are total time steps defined? Is it here? I feel like it's I'm seeing some redundancy. Or also here. Seeing some redundancy. Both locations find values, but the command line argument parser takes precedence over the function. Okay. Okay, I see. Well, let's try it. Python Bipedal sb3 ppo slash time steps 10 million. Oh, there was one more thing we could do too. I probably called it incorrectly. Choices. Oh, I see. So we have algo PPO time steps 10 million. Okay, and now this is running. And okay, and now the thing is, we could do the same thing in multiple terminals. So SB3, LS, SV Bipedal, CD-SB3, and then we call the same thing Bipedal SB3.py, algo, A2C, time steps. Right, so we can initialize the. Oh, I see. Okay, it's probably case sensitive. That's A2C, time steps. Yeah, and then we're gonna do that for all of the options here. And I don't know if the computer is gonna melt. We'll see. Bipedal, LS, CD-SB3, and it's like Python, Bipedal, SB3py, algo, stack, time steps. Oh, I guess one more thing we could tell SB3 is we're on a Mac. I think by default it's gonna recognize the CPU. I don't know if there's some Mac specific thing to do here. Probably not. But you know, Bipedal SB3, Python Bipedal SB3py, algo TD3 time steps 10 million. I don't expect to actually run 10 million time steps. This is just like me saying like, oh, we're gonna run a lot. I'm gonna kill whichever is like, I'm gonna run all 4 algos here we have, and I'm gonna see based on the mean reward curves which one's actually working, and kill the ones that are not working. What is the command to launch TensorBoard? All right, and then one more terminal to run TensorBoard so we can see those learning curves live. It felt a little laggy there. TensorBoard log0logs. All right, so from there we should get these here, and then we can go here, and we can go here, and then the other thing we should check was here. Yeah, CPUs we're running kind of hot. Honestly, this feels much more. I mean, we have memory to spare. CPUs are not maxed out like they were with Neat, which is interesting. Okay, and this is what TensorBoard looks like. I don't like the default colors, so you should change it. But we have mean episode length here, and actually mean length. What? Shouldn't these two be the same thing? Eval rollout. Eval rollout. Let me ask, what's the difference? In TensorBoard, what is the difference between and comes from the actual training episode. So rollout comes from the actual training episodes. Okay, mean eval comes from the evaluation call feedback. Shows episode run purely for evaluation purposes. Uses deterministic non-exploration. Okay, so it looks like we want eval. Okay, so eval sounds good, but we don't get values for SAC and TD3. For SAC and TD3, why is that? Probably something to do with the algos themselves. They are off policy, they just replay buffer and they need different evaluation parameters. This modify. Okay, let's ignore that. Ignore that for now. Okay, let's focus on the episode mean reward here. I do hate the commands here. You click here, it doesn't actually work. You know, there's still a tranche of a curve out. Anyways, what we want to see basically is a episode reward mean that goes up. What is the maximum? What is the maximum theoretical reward for this environment? I don't know if there's one actually. I should just check the docs myself. Actually, haven't we talked 300 points, right? 300 points. Good agent. Yeah, 300 points. We're here, right? So 300 points. Yeah, we can see here that the episode length for PPO has like kind of like has plateaued, but here we keep going up, and so we should be able, I think, to evaluate some stuff here. Bipedal. We have our evaluation. Well, we do need to open another terminal, but we have Python evaluate bipedal pi algo PPO. The best so far, right? It's still training. Oh, models PPO back normalize PKL. Load the safe normalized parameters. I'm not sure. Let's ask the AI. The order request we could try to load normalization that doesn't exist special path. The file is typically created during training and is needed to provide. Here's how to fix. Does bipedal sv3pi create the PKO file? I don't think so. Yes, it does create a mechanism during training, especially happens in training model. Oh, but it only saves the final model. I see. So the PKL is only created for the final model. Okay, so now it wants to patch this code. Render false callback. I guess a little late for that, man. Okay, so I guess we're not gonna evaluate anything for the time being. Okay. You can already tell that these SAC and TD3 not really going anywhere, and A2C SAC struggling. But on the other hand, PPO is plateauing, which is not something we want. But we're really not even like a million in, and we said we're gonna run it for 10 million. What we could do is we could kill TD3 and SAC because it doesn't seem to be going anywhere. But you know, okay, some cores. Okay, I see. I think we keep these running for a little bit. I do intend these to get to at least 1 million. So I'm gonna probably walk away for a few minutes and come back to it. So I'll be back later.
2,000 years later.
I said I was gonna I said I was gonna pause it while it trains and then come back, and now it's 2 days later, uh, and we're only seeing the results now. So what happened was, yeah, I left it running. Actually, I made a couple changes on the code. Let me change this to light mode. But I made a couple changes in the code. I think mostly I removed normalization of the observation space. So if you're not familiar with what that means, on the observation space, we have a range of values, and sometimes, some values could be very high. Like let's say, a sensor gives a value in the range of 0 to 1,000, and another sensor gives a value in the range of 0 to 1. So the 0 to 1,000, 1,000, the number 1,000 would weight heavier on the training process, and so you can normalize these ranges. So basically, all observation space inputs are the same. But in the case of the bipedal walker, this looks like around the same. Like there's a 3, there's a 1. It doesn't look too bad. There's a 0, there's a -1. The range doesn't look too bad. So I removed normalization, especially because when you normalize, you basically you train your model and so on, but you also keep a separate file to basically translate from the normalized values to the actual values. And I was having some issues with saving that, even though it sounds very simple. But I just like, I was just like, it was easier to remove, plus it sounds like we don't need it. But yeah, anyways, that's basically the only thing I changed. And then I just left it running for 10 million steps, I think. 10 million steps or episodes? Actually, that's a good question. Let's ask. Bipedal. Does these run for 10 million steps or 10 million episodes? But anyways, now we can look at the result charts for the first time. And also let me pull up our to-do list here, right? So last time we were doing these. We've done these. We've solved the bipedal walker. I mean, I think we've done it. That's what we're doing right now. And we've also tried different algos, right? So we have like 4 different ones there, including PPO. So let's see. We run it for 1 million time steps. Well, that's not true, because I told it 10 million time steps when calling the file in the terminal. But that's fine. So we ran for 10 million time steps. So that's what the x-axis is here, time steps. Anyways, what do you notice from looking at not rollout but eval? So we have the mean episode length, the average episode length, and then the average reward for each time step. And then we have PPO, A2C, SAC, and TD3. So I mean, okay, let's start with PPO, I guess, right? What do you notice here in PPO, right? So obviously, the first thing that's become obvious here is that the mean episode length decreases, which, this in theory could be good. It could mean that the robot, just to recall, right, it's like a bipedal thing, right? Like it's a bipedal walking through a maze, and the episode is done either when it reaches the end or when it fails. So the episodes ending sooner could mean like it's learning to move faster through the thing, which is a good thing, or it could mean it's failing faster. But I think it's probably that, and we're gonna find out. We're gonna run it, but and then we have the mean eval reward. And what do you notice here? Well, actually, okay, back to the episode length. What do you notice here? It's like, probably like after like 5 million, 6 million time steps, these kind of like plateaus. We probably didn't have to, we could have cut training time in half, and it probably was fine. And the mean reward here, I mean, obviously what do you notice here? Like seems like, I don't know, like 500K time steps in, our min reward was already like 300, and it's basically flat at 300 forever. It's a little spotty, but 300. And why is it 300? It's because you need to get 300 points in 600 steps to win the episode. So basically we're being successful in the episode. Right, so now the reward plateaued, the episode length kept going down, which I think it's good. And so if we were to look at the results here, and bear with me because like again it's been a few days and like my memory is very short, so maybe I forgot already. How to evaluate this stuff, but yeah, so I wrote an evaluation thing here. Let me see, what are the parameters I can pass? What are the arguments I can pass? Code base. Anyway, so if I execute this, it's going to show us the I think the best model for PPO. I think best model, first of all, I think it's based on reward, and because the reward plateaued, I don't know on which time step it's going to show us, right? So so we need to figure that out. I can pass a different argument for time step, pretty sure, because we do have checkpoints. I think we have checkpoints. I think we have checkpoint. Oh, we might not have. Alright, there's a chance we don't have checkpoints. Maybe we just save best model, but okay, let me run these and let's see how it performs. It's like basically just one leg. It's very funny. That took 1,000 steps to complete, right? So if we go here on our chart, 1,000 steps, it's somewhere in here, right? So apparently we went under 800 episode. I think episode length is measured in time steps. That would make sense to me. Small path. Let's see if, okay, it's coming down. Let's see if I can checkpoint. I don't know if we store checkpoints. Yeah, there's no checkpoints. Okay. Anyways, so that's what PPO gets us. Like I said, I think this is probably what we got, kind of like a million episodes in, a million time steps in of training. It's not bad, right? Like it does move forward, it doesn't fall, but we kind of wanted to like walk like a bipedal, or like the legs alternate, and so that's not what's happening. All right, let's check A2C. All right, so here, okay, what do you notice? Reward minus 100, right? It looks like this never went anywhere, and we very painfully ran it for 10 million time steps here. The episode length all over the place. You know, 0 immediate failure, and like over 1600, which is the max. So failure, just failing left and right. But let's just see it. Let's see what it looks like. The best model they had for this algorithm. And yeah, it looks like trash, of course. I mean, it looks like it might be successful. Unless it's gonna run out of time. By the way, I went to watch Gladiator 2. It's funny how close to Gladiator 1 it was. It's basically, I think it's been so long since Gladiator 1 that Oh yeah, it ran out of time here, so that's why it lost. I mean, the walking is okay, but yeah. Okay, so this one never worked. I'm like a little curious to know why it didn't work. What about it? What's A to C? In RL, what is the A to C algo? Let's see. And meanwhile, we can see SAC episode length again. Plateaus like 3 million time steps in. Reward function over 300. I don't even know how that's possible. This looks very good. This looks very, very good. The time step, the mean episode length is even less than PPO. I'm excited for this one. Oh yeah. Oh nice. Ooh. The legs were kind of like almost alternating there. If I had to run something on my robot, it would be these. But again, the legs don't alternate. That's very nice. I like that. Okay. A to C. Advantage actor critic. 70%. Okay. Training loops run. Okay. Advantage. Parallel mechanical PLC. I'm so new to these that it's hard for me to tell these things apart. What about TD3? Oh, that looks very nice also. That looks just as nice or even nicer than SEC. Let's try it. Yeah, that's very nice. Yeah, good time. 678 steps. This is doing better than our PPO policy. Total reward 329. I don't know how that's possible. 328. Maybe I forgot what the reward is. Isn't it reward? For given model totaling 300. Okay, plus points up to the front if the round falls against I see. Okay. Yeah, so a more optimal model agent will get a better score, right? So SAC is the most optimal apparently. How would you compare SAC, A2C, TD3, and PPO? The application is robotics. Just give me a table. Don't give me all these present the results in a table. Come on. Oh, I was gonna do a table anyways. Interesting. Exploration, moderate, high, low. So these are our two best performing, right in the middle. Both are high efficiency, both are off policy. So off policy seems to have worked better. SEC for tasks requiring smooth control, robust learning, efficient exploration. That's very interesting. I think we will probably continue to experiment with all of them. The other thing is like now we know that 10 million time steps is probably too much. Like we can probably cap it at around like 3-4 million. The other thing I'll say is that TD3 and SEC do take longer to train, especially TD3. That's the one I remember took so long. And again, like that Disney paper used PPO. I think I need to look more into the math difference. Can you explain the difference between all of those algos in layman terms using only a few sentences? A2C learns to a trial and error, but throws away old lessons like cramming for a test and forgetting everything after. Relatable. Doesn't work great. I know that. Explores a lot by trying risky moves while saving all past experiences efficiently. This sounds good to me. Okay. Takes away steps to improve. I mean, even within PPO, there were a lot of variables that we could have optimized, and we didn't. We just run the most vanilla thing. So I don't think these results are good enough to be able to say like, oh, going forward, you know, SEC is the way to go. Watch us. Soft actor critic. All right, but I think going forward, it's safe to say A2C is not the way to go. I don't know why. Okay. The other thing I was gonna say, and maybe this is not as relevant. This is the first time I'm seeing the results. I was gonna say, like, what if we remove some stuff from the observation space? You see how there's a laser sometimes? That's a lighter. So if you see the observation space here, of course it doesn't tell you. Bipedal walker. Observation space. Yeah, observation space here, you know, whole angle. Like I was, I guess, a little uneasy about having the 10 lighter readings. This feels like cheating. We don't need that. Just don't need that. Yeah, it feels like, do you even need ground contact flags? I don't think so. So we could remove some of these from our observation space. And I mean, my motivation is like the fact that we don't have any of those sensors in our real life robot. So I was curious, like, how would it perform without any of those? And then of course the other thing is that that it doesn't alternate its legs, right? So, I mean, other than that, I think it looks okay. But it's like, how can we think of the reward function to... it honestly does a good job. It's just, you know, could we make it look better? And so that's when you got to start thinking about the reward function. And I mean, they don't go into great detail here, but I mean, I imagine there's a repo somewhere because it's all open source where Gymnasium, GitHub, where they'll specify these bipedal. Reward. I think that's an example. Here we can see the penalty of applying a torque to the reward. It's very small, 0.0035 times torque. Oh, it's normalized to about -50 is interesting. Yeah, so I was curious to see how it would do if we just remove some of this observation space here. And we can try these. No. I'll just do a quick experiment, very quick, SP3. Experiment. I guess. Experiment. Bipedal SV3 fine. I'm just gonna copy the same code, and then you basically just need to change a couple lines in order to change the observation space. By the way, all of this is on the GitHub repo. All this code is on the GitHub repo. You can go see it. Okay, so on the training file here, which is this one, train the model. There's gonna be an observation loop, a loop with observation or ops, yeah, OBS. Load the model for episode while not done. Yes, right? So here, oh no, that's the, wait, evaluate model? I don't think we're not using this. I guess we don't need that though. We could remove all of these sections of the code. Don't need that. Train model, yes, here. Man, I'm gonna remove these. Don't need that. Don't need. Okay. Okay, no one has observation. No, okay, perfect. That's weird. But bipedal, add hyperparameter, tuning okay. Yeah, these are all things, parameters we can pass when we execute the training file. I think it's somewhere in here, but just check in here. These are parameters for each algo. All right, somewhere in here, create and wrap the environment. Callback. Now let's ask the AI if I want to modify the observation space. Where is the best place to do this? The observation space during the training run. I simply want to remove some parameters, some values the environment returns. I don't know if it's gonna be straightforward. You want to create a custom wrapper for your environment that filters the observations. The best way to add this would be right after creating the base environment, but before wrapping it with monitor and dummy. Let's see what this looks like. I swear I clicked apply and it didn't apply. What's going on here? Oh, I gotta select here, okay. We already have Gymnasium. Oh, I guess observation wrapper, custom observation. Oh, interesting. Environment custom observation. Okay, that's a good start, but obviously we need to tweak this. So thank you. Obviously, always thankful. Okay, so I'm just gonna say I'm gonna put this down here. Try not to block the things. There's so much going on the screen. Like that. Okay. Thank you. The observation space from the Gymnasium bipedal walker is of type yes. The observations are enumerated from 0 to to 23. I want to get rid of observations. So let's get rid of the ground contact flags, which we don't have in our robot. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and then the lidar. And this is a good place to start. And after that, I want to see how it performs when, because right now we can, for each joint, we have angle and speed. What happens if we only have angle, which is basically the case for our quadruped robot, since our servos input is only position, right? So I'm curious to see if this makes training like super hard or if it doesn't matter. All right, let's see what it says. Hope you modify. This will reserve stations raised from box 10 to box 12. Keeping. Okay. Oh, okay. I see. I actually made it very easy. Custom observation wrapper. In itself. Can you explain to me how custom observation wrapper works? Okay, which is a Gymnasium utility class design. Yeah, there's a lot of really good Gymnasium functions and stuff that you can use. There's already a lot of the infrastructure built that every time I ask the AI to do something, it calls this obscure Gymnasium thing I've never heard of, and it works great. It's like, oh, someone already thought of these, of course. It's just very basic stuff. We just need to know how to modify the observations, observation wrapper, observation wrapper. Takes two parameters, the environment and which instances to keep. That's great. Super sets up base wrapper stores. Okay. Well, let's try it, right? So what worked great last time? Experiment description MD. So in this experiment, we remove the following observation parameters. What do we say? 8, 13, 14, 15, 16, 17, 13, 14, 8, 13 to 23. This is equivalent to removing the lidar readings and the ground contact flags. You can view all parameters here. All right, so that's one experiment to run. CD Bipedal, SV3 experiment, LS. All right, and so now, I don't know, do I want to run PPO or TD3 or no, SAC? We could run, Python, Bipedal, SV3Py, Algo, SAC. And we could see how it behaves. Oh, time steps, I guess. Time steps, 3 million. So we could run these. And while that runs, oh my bad. I guess the one thing is that I think our tensor board's not gonna catch these, but it's fine. Okay, so we have that running, and while that runs, we could run another experiment 2, and for experiment 2, I want to remove the joint speeds. 7, 8, 9, 10, 12. Right? So 5, 7, 10, 12, right? This is going to removing the ladder readings, the ground contacting, and the speed readings of the joints, right? So we have that, and so we have to go here and to our list of things to keep. We gotta remove all the speeds, which is 5, 7, 10, 12. So 5, 7, 10, 12. 5, 7, 10, 12. So now that we have that, I guess we could I think that's all it takes. So now we can go to this directory. Oh my bad. Algos, SAC, timestamps. Oh, I always forget double dash. Timestamps, 3 million. Now, the question is TensorBoard catching these? I think no. The answer is no. I think the answer is rightfully no. Because we're in a different directory. So now, how do I initialize TensorBoard for this? Yeah, okay, let's run some TensorBoards here. CD experiment to TensorBoard. Oh, that's weird. I thought we already have a port there. I guess, does it just, oh, okay, 7. And then here, CD experiment 2. TensorBoard, nocture equals logs. And then we have an 8 here. So a bit messy, a bit hacky, but see if I can remember these. Okay, I can kind of remember. Okay, so which one is which? This one down here is experiment 2. I don't know how I can. Okay, just remember experiment 2 is blue, experiment 1 is red. All right. Right, perfect. And I mean, okay, this just started, so you need some patience here, but I don't know, predictions. What do you think is gonna happen? The mean episode length for experiment 1 is higher. But okay, let's focus on rewards actually. Okay, rewards both are still on negative rewards. They're they're doing their thing. And computer is not melting, which is nice. Always good not to melt. That's good. No, okay. All right. Anyways, while that happens, let me go back here. Let me mark this done. The last thing I wanted to do in this video, because I think it's getting a little long and it's just me talking to the computer, so it's maybe not as entertaining, but loading our own robots into this environment, right? Because right now we're using, first of all, right now we're using the Bipedal walker that was made by OpenAI, I guess, and it's on 2D, right? what we want is to load our 3D model onto this environment. And I think there's a few virtual 3D environments you can use. There's Isaac Sim by NVIDIA. There's PyBullet. There's MuJoCo. There's one more. I always forget. The one that ROS physical sim. Gazebo. Yeah, you don't want to use that one. That's all I know. I remember Gazebo from university. Gazebo sim. Yeah, I mean, I don't know. It's like, feels like for RL, MuJoCo is pretty popular. Isaac could be good. MuJoCo works pretty well with Mac, I think. I can't remember if we've already talked about these, but it's been too long. So this is gonna be like the next one, another folder. I'm gonna call it MuJoCo. And I mean, while all this stuff runs, I'm just gonna kind of show you what MuJoCo looks like. Show myself also. It's not like I have a clue here, but I would like to use the Gymnasium library and MuJoCo to load a virtual environment. By the way, maybe we should check the MuJoCo docs. Documentation. I think Google DeepMind is. Did they fork it, or do they? Do they kind of like quote unquote own it? It's possible. Gymnasium. It's weird because I thought you could import MuJoCo from Gymnasium. I don't know how that works. Okay, well, this takes us back to in the Gymnasium docs. There was a MuJoCo section, which is how I know MuJoCo, and they had all these models here: a humanoid, walker. I guess walker is like probably like a good place to start. You can use this line for the environment. I want to render this environment as human and input random actions. Like the basics. And we're just gonna have the AI, do the basic work for us. Meanwhile, we check here. Okay, this guy didn't move. Okay, there it goes. Just stuck here. Rewards. So rewards are still negative and not trending great. But it's still early. We're like, yeah. By the way, the other important thing to know, I guess we're training time steps. We said 40,000 time steps. Yeah, no, that's fine. It's just, I'm pretty sure that there's an implication of time per time step, right? So you could translate time step into seconds, actually. I feel like when I talk to some people who know what they're doing, they always like to talk in terms of time, because it's more grounded towards physics, I guess. Like something's dying there. Okay. So let's see how it did. So Gymnasium, why do we need NumPy? Create environment, yes. Human, yes. Observation. Okay, initialize it, run the environment. Does this environment have, I feel like all environments have a reward. Yes, the reward healthy bonus. Okay. Why do we need NumPy? We're not using NumPy. That's kind of weird how it does that. I mean, not the most useless things you have, but no. So these are random inputs. It's funny because the legs are overlapping. There's like no collision. Collision. No. Collision. No. In the hopper environment, what's the hopper? Oh, so hopper environment was a single leg. It's interesting. I don't like that the things are colliding. Healthy walker. Okay. I guess what's the termination? Any state of the values is not for the occurring afterwards is not in the closed interval length. The absolute value of the angle observational if it's not enclosed. Okay. 1,000 steps. Yeah, that's good. We're already at 1,000 steps. Arguments, observation space. Okay, angle of choice. Okay, wow. Angle velocity. I'm very curious about this experiment we're running on the background, because these observation spaces are huge, and it's like, do I basically just want to spam sensors in my robots? Is that like the takeaway here? Is that what I'm supposed to do? I wish I could set an alarm here for it to like alert me, like, hey, by the way, like pop up, like reward function has crossed 300, kind of like with how they do with stocks. That would be cool. Okay. Anyways, I don't know, like, is there any point in showing that, we can train these? I mean, I guess it could be interesting. Does this environment allow object collisions? Yes. Ground contact. Okay, yeah, soft collision. I see the legs colliding. Is that allowed? Yes, self-collision between small corners are allowed and are currently part of the physics simulation. Okay. Okay, I don't think I care. I just want to show you a 3D environment. Anyways, then the next question is like, how can we import, instead of using the Walker 2D, how can we import our own model, right? Like in our case, like how can we go to OnShape and import that robot? Sorry. And I know K-Scale has written about these on their docs. There's like a whole thing. I mean, see, I haven't tried, but they made it sound like it was hard. Now it's like, I don't know, man. How hard could it be getting started? Retrofitting your garage. Build guide, introduction. Okay, all the docs are empty, but URDF to MuJoCo, right? So they built, I think this is custom. They built their own. Yeah, they own this thing. Convert URDF to MJCF XML. I actually don't know. I guess I'm trying to do OnShape to URDF first. Step 1, URDF, OnShape to URDF, and then URDF to MuJoCo, which I assume that last part is easy peasy. Command line that. Okay, that seems super straightforward. I'm gonna star this for later, I guess. Let's go here, MuJoCo. Okay, URDF to MuJoCo MD, and I'm gonna rate these. Okay, that's for later, just so I don't forget. We're doing an OnShape to URDF right now. That's the key question here, right? And they also have a library for these. which is nice. Except documentations. Okay. All right. Here's an example of a robot converted using the KOL command line interface with the input OnShape model on the right and the output URDF on the left. To reproduce the above example, you can run the following command. Actually, kind of curious to see what this looks like. Again, I've never done this. I've heard that your OnShape model has to be formatted in a certain way. I've heard that OnShape is very picky, right? So if you see here, you know, it's an assembly with assemblies inside of it. These assemblies are okay. And you have primitives. Oh, interesting. I guess they just model everything in one file because they don't care, because they're gonna quote unquote quote the joints in MuJoCo. Question mark. Oh, these moves. How the hell did they do that? Oh, that moves. Oh, I guess it's an assembly. Actually, that makes sense. All right. Well, nothing looks crazy here to me. So, all right. Why don't we go through these docs here? All right. People install these things. Done. I'll show again. All right. What happens if I run that? In order to use this tool, you must first set an OnShape API key here. Would you like to open the? Yeah, sure. Open the. Yeah. You guys are gonna steal my API keys. Oh no. No. That sucks. All right. Fine. I'm gonna have to request. All right. So this might not happen in this video, but I tried. All right. I'm gonna email OnShape like a boomer and be like, oh, can I have access to the API? No. Okay, whatever. There must be another way, right? Run. Wait, what was the command here? Run. Yeah. Download. Only download from OnShape. Download from OnShape and post process. What? I wonder how it download. Like, what's the? I wish it would tell us. What's the? What format does it download in? Oh. Very disappointed OnShape. Very disappointed. So this is our dog. You know, there's a lot of mates I still need to fix. Obviously, look at the legs; they don't match. And I remember something about only being able to use fastener joints when moving to MuJoCo. Let's see if it mentions anything here. Where is it? Here, joints. Mate, sorry, mate. Fastener mate. No, it doesn't say anything. Did I read this on their Discord? Man, I don't know what's going on. I'm super tired. It's been a long week. I thought I was moving tomorrow, but turns out I'm not. It's been kind of stressful. Let's see. Fastener. No, I didn't read it here. Anyways, I'm gonna get API access to that and actually OnShape to URDF. I guess a lot of people have stuff for these. Yeah, a lot of people seem to. Oh God, Arrows. robot automation too. Anyways, we're not gonna make a video of me watching a tutorial, right? That's not what's happening here. So I want to let these run for a little bit longer. And after that, actually, let's see where we are right now. Yeah, seriously, if someone could make something that, you know, when the reward reaches something, it takes my phone or something, that would be great. Tensor reward, notifications, text, SMS. Yeah, no, okay. Anyways, I want to stop recording. I'm gonna come back when we're at like 1 million, 3 million, when it's either clear that this is working or failing. All right, and then we can review the changes. I guess like one of my concerns is like, do we have enough sensor data? Realistically, like we have no sensor data, right? We have like, we know the servo position, that's it. We're gonna add an IMU, which is gonna give us like 6 degrees of data, right? So it's a 6 degrees IMU, so we can calculate pitch, yaw, and roll, and then their derivatives, right? So how fast we're rotating, plus acceleration in 3 axes, and their integrals, right? So we can figure out speed in a way. So we could have all of that stuff, but other than that, we have nothing. So we need to figure that out. And let's see. I'm gonna write this down. No. API axis LOL. Yeah, so I guess part 13. So to do here, we need to install the IMU. We need to actually install the IMU and import robot to MuJoCo. Fine. Attempt to train robot using RL. Attempt to train robot walk-in model using RL. Install MU. There's like a bunch of like hardware upgrades here. So we have servo horns, we have shoulder horns, I guess knee horns, shirt horns. We have a 7 upgrade, I gripped servos to 7B. That's another thing. The other thing is like, I just realized like the switch we use to turn it on and off, it's actually not rated for enough power for these applications, so it's at risk. I don't even want to change it now. So there's that, and then we can potentially move away from Arduino. Potentially. I say potentially because there's no immediate reward to these other than like maybe, just maybe, the wire mesh will get a little bit better. But on the flip side, there's some risk that the board that we order cannot handle the power requirement from the servos. It's a little, like, it's definitely like very tight. And I think at the end of the day, it's a thermal issue. Like, it's gonna be a thermal issue for the board. So the upside is like better cable management and moving to MicroPython instead of Arduino code, which is not a huge upside. And then the downside is like maybe like the board doesn't work. What else is the downside? Yeah, so there's it's like why would we? But at the same time, it's like interesting, and I feel like it's a good learning opportunity. Like, I'm interested. So this is what we need to do on the next video. So it's gonna be action packed. It's gonna be one of those 12-hour videos you guys love. Anyway, so I'll be back in a sec. All right. So this training run is done. So here are the results. And let's take a look. It's been like a full day, by the way. I don't know if the SAC runs, like the training runs, take so long because we're CPU constrained and we should be running these on GPUs, or we need even more CPUs. But it does take a while. And you can see here, these are the mean rewards for both experiments. So one experiment, so we removed the entire LiDAR observation space, and we also removed, there was one more thing. There were, yeah, well, okay, we wrote it down, so I can just go and read it, but you can see here a big change, right? So this reward function here, it basically plateaued at, at around 300, which is what we want to see. And actually we want to see a number slightly higher than 300. So it goes to 326 here, which is good. But then here on the other run, the highest we get, it's around 28, right? So ideally I would have like just kept training that one for a bit longer. And then I have here the reward function, the reward curve for the initial experiment with the entire observation space. And you can see here, it basically gets to 300 much faster at around like 500,000 time steps, right? And here with the reduced observation space, just under 500,000, and here it never gets to it. So that's interesting. I'm not sure exactly what to make of it, right? Because both of these experiments had smaller observation spaces. For one of them, it worked. It looks like it improved our rewards, our mean reward, and for the other one, it looks like it just didn't, and it needed more training run. So let's look into that. But actually, let me take some notes. Like learnings from here, it's like if I was to write what did we learn, one of the things is we should not be constraining our training runs based on time steps, right? Like the 3 million time steps on this training run was arbitrary. It was just because the first time around, like, we trained for 10 million time steps, and it seemed like too much, right? Even PPO, SAC, TD3 were all like basically plateauing the reward function at like 3 million in, right? But that's not always the case, especially as we change the observation space. So what did we learn? Ideally do not constrain the training runs based on time steps, right? So a better constraint, ideally, like, I would have no constraint. I would just observe it and keep track of where our reward and our episode length are. And when the episode length is plateaued and the reward has plateaued, then I would stop it manually. And the next step, I guess I'll write this here. Just monitor the curves and stop it when it makes sense. Reward and episode length have plateaued, right? Now the other thing is that I haven't done is save model for every evaluation checkpoint. I think that's what evaluation callback, right? So every time, so these curves look smooth, but they're actually discrete, right? So I think it's every 10,000 time steps when we do an eval run, and that's how we calculate the mean reward. We should be also storing the model for that. Right now, the pipeline is built in a way where we only store the best model. So whether there is like in the middle of the training session or at the end, we store the best model. And I think we're not using some custom logic. We're using just like the default SB3 functions. And I think what happens is when SB3 talks about the best model, it's entirely based on reward. Whether it's like, we do not care if the reward function, it's maybe like 1 point more. We will take 1 point less on rewards if that means the episode length is like significantly shorter, right? Which is what we saw here with PPO. If you see this, if we compare these two curves, I'm just gonna take the entire screen. If we compare these two curves and they're not aligned, the x-axis are not perfectly aligned here. Let me try to. But you see, like maybe like the max reward was somewhere here, but the episode length kept going down. So the model I want to use here would be somewhere down here, but because we only saved best model, pretty sure we saved the wrong model, right? So there was a better model, but not as measured by the mean reward. So I would rather save all of them, right? We spend the time training, so I would rather have all of them and check multiple one of them. So we do gotta make that change to our pipeline the next time we're training something. Not just best model based on mean reward. Yeah, so that's what we've learned so far. So now let's take a look here. Let's read our notes and let's make sure. Oh, by the way, I also figured out how to go from OnShape to URDF to MuJoCo. I'll show you a few things real quick, but you know, that'll be on the next video because this video has already gone too long. The thing with like training anything on video is like all these training ranks take so long. It's like I start training one day and I have to wait till the next day for it to be done. And I think this is like a third or fourth day of this specific video. So ideally on the next one, I'll start the video by training something, then maybe I'll do some CAD, some 3D printing, and then we'll review the results of the training or something like that. What else was I gonna say? Well, I guess another learning was that we removed some observation state parameters, but we didn't verify that we actually removed the right ones. Like it could have been a very simple mistake, but verifying the observation state would have been a good thing. Verify observation state when making changes. I mean, obviously that should go without saying, but I just didn't do it. I guess I was rushing. All right. Yeah, I remember writing some notes here. It was on SB3 experiment and experiment 2, and then experiment 2 is we removed the LiDAR readings, the ground contact flags, and the speed reading at the joints, right? And so experiment 2 is TensorBoard localhost 86008. So it's this one down here, right? So experiment 2 is the one where we remove more things, and then experiment 1 we just removed the LiDAR and the leg contact flags, which I think that the contact flags would be kind of like a boolean, maybe not a boolean, but maybe like a 1 or 0. Actually, let's see. Let's verify. I think the best place to check this is the repo. Oh yeah, the other thing was okay. Yeah, I'm just all over the place here. I'll wait. I'll show you guys this later. But anyways, why don't we just evaluate these results first? So yeah, if we wait, are we still running? No way. All right, so experiment 2, right? So we go just Python and evaluate Bipedal Py and Algo SEC. That should do it. Yeah. Oh, okay, I see. So we changed the observation space, but we didn't update our evaluation function needs to change as well. So I'm just gonna ask the AI to do that real quick. Can you change the evaluation Bipedal Py so that it uses the new and smaller environment observation space as defined in Bipedal SB3 Py. Alright, this is the issue with naming all your files the same thing and just putting them on different folders. Okay, now we do that. This should be straightforward. I'll modify, yeah, because like the issue should be here, I think, somewhere. we are expecting 24. Let's see. Custom, oh, okay. Yep. All right, let's see if that works. Yeah, that makes sense. Run these. All right, so this is experiment 2. So remember, this reward function reached 300. Actually, let me check the, so this is this one here. And the episode length was still going down. But of course, we actually do not know, or I do not know, which one was the best. Okay, it's completely stuck here. Let me, oh. Total reward 9, so that's really poor. That actually looks much more like this one here. Yeah, that sucks. Let's take a look at the other one. So I think this should be experiment. Yes, okay. Okay, so Bipedal, SV3, just make sure equal. All right, changing the evaluation function again here. Yeah, I think what really is like causing us pain is this point here. Save model for every evaluation callback, not just best model, right? Because we are kind of like not sure which one we're looking at, other than like the all we know is that the reward is good, but the reward could be hiding some of the truth. So let's run this evaluate by Bipedal pi. Oh yeah, sorry, that's my bad. That actually looks much better. I actually think we probably mixed up our reward curves. This looks much better. See, okay, this makes much more sense to me. So of course, experiment 1 is the same as, like, it doesn't have lidar and it doesn't have contact flags, but it does have joint speed. And experiment 2 doesn't have joint speed. And the reason why experiment 2 doesn't have joint speed is because the robot dog will not have joint speed, right? Because we have servos. We could kind of like derive joint speed, but I was trying to figure out if joint speed is like a crucial thing for training, and it seems like it might be. But of course, there's so many variables we can play with here, right? So maybe SAC, the algo, the SAC algo is like really, it's like very sensitive to having like speed inputs, and maybe PPL would do better here. I'm not sure. These are all things we can try. But oh yeah, see these rewards 300. Yeah, so our mean learning curves mean reward curves were flipped. So yeah, so really we need to make these 2 changes here. All right. Wait, I'll be right back. All right, so continuing here, our notes. I think going back to what did we learn, point 4 here should be treat every training run as an experiment. And what I mean by this is we should be documenting parameters and have like observations plus final observations. And so with that in mind, the observations for the 2 experiments you run here, so SA2 experiments, experiment 1 and 2, right? So I would say, for example, here, experiment 1, we removed lidar and contact flags from the observation space for the Gymnasium bipedal walker, B5, I think. B5, bipedal, B3. Experiment 2, all of the above. Bladder, contact flex, and joint speeds from the observation space. Trained using SAC Algo for 3 million time steps. Same for here, right? And then results. Right, so what did we observe? Going back to experiment 1 here. Experiment 1. Right, it's pretty good. That will be my observation. It's pretty good. First of all, mean reward past 300, which is success for this environment, right? Episode length of, let's quote the exact figure here. I'm pretty sure it's this one here. Episode length of 800, which is on par with it's actually higher. I'm gonna call this experiment 0. I'm gonna add an experiment here. The previous round's gonna be experiment 0. Default environment 10 million. Trained SAC, PPO, TD3, and A2C for 10 million time steps. Results. Right, what did we observe last time? I'm gonna break it down by model. TD3, A2C, SAC, right? So PPO. What did we observe PPO here? So mean reward curve plateaued at that looks like just 300, at around 300, and this happened after around 600k time steps, right? That's what happens. And then mean episode length continued to decrease until it plateaued at around that looks like, kind of like 700-ish, low 600, 6 to 700 after. Maybe we can call these like 8.5 million time steps. Yeah. Okay. Let's just quickly summarize all of them. TD3, because we'll always have the data, but I think we're not going to look back at it. And the other parameters we should be capturing are things like end steps and all these other parameters that you could set for each algorithm. Basically, this section of the code here, right? This stuff here, which can be tuned. We should be capturing these eventually. We're probably not going to do it now, but yes. Okay, so TD3 reached a value reward. Okay, so mean reward curve reached 315. After 1.6 million time steps and plateaued. Mean episode length plateaued in like the 600s, in the mid 650s, 600s after, like 4 million times after, something like that, right? So this is important as we compare with the next, you know, with our two experiments 1 and 2, right? So basically, how did removing things from the observation space change our results? All right, next A2C, right? So this is a mess. I don't even know what to say. Yeah, okay. So the mean reward plateaued at -100 after 2 million time steps. Basically, that's what I'm seeing. I don't know if this is correct. The mean episode length 50 seems wrong. Mean episode length plateaued at 50 after 2 million time steps. Okay, interesting that these two are the same. I guess that makes sense. I'm not exactly sure why that is, but this of course this was the worst we saw. So, and then we have SAC, which was best performing. So mean reward reached 330 and plateaued after converge. I'm not sure what word we want to use. No, I'll say 1 million time steps, right? So that was really fast, I think, in a way, compared to all the other stuff. And then here, the mean episode length reached, you know, again, the mid 600s after, we'll call it 3 million time steps, and plateaued, right? So the minimum episode length for SAC appears to match that of TD3. Both are like out policies, I think. Like in RL, TD3 and SAC are both policies. Let's see if ChatGPT can fill in the word. Off policy algorithms, that's what they are. So it's interesting that they had this similar results. All right, so now we jump back. We don't need this anymore. Let's go back to our experiment 1, right? So mean reward passes 300, which is success for this environment. That's not this curve, it's this curve, I think. Yes. Plateaus around 320. Plateaus at around 320. Maybe after it actually keeps increasing here. Keeps increasing. After 1.5 million time steps. Achieved after 2 million time steps, right? So the mean episode length 800. It never goes as low as 650, which we showed before, but it's important to note that these did train for longer, right? So we end these prematurely, potentially. And now here, right? So now these curve here, basically these here. So, well, okay, well, first we'll comment on the reward function, right? So the mean reward, highest value was under 30. And that was 3 million time steps in. Looks like this was ended prematurely. So it seems like with less data on the observation space, it might take longer to train, potentially. Like I said, I still think it's worth to run this experiment with different algorithms, see how sensitive they are. The mean episode length was basically 600 throughout the training run. This is bad, and this is bad as the environment terminates the episode at 600 time steps, right? So we could conclusion of experiment 1 and 2. We probably ended these training runs prematurely at 3 million time steps. No reason why we should not let it run to 10 million. The smaller observation space appears to require longer training runs, aka more time steps. And then we wonder if other algorithms, and then basically Bipedal and TD3, would perform better on the smaller observation space. All right, so that's all I'm gonna say for the training runs for these. I'm gonna actually close all this stuff. We're closing this chapter, and then quick note on going from. I've been watching some trash. Where is it? All right, so basically I was watching this tutorial on how to go from an OnShape to robot. Robot being like, URDF basically. URDF being the format that you need to import a robot geometry into Pybullet basically. Like it's like this is what let me show you what a URDF looks like. This is what a URDF looks like, right? Where you basically define, the parts, the mesh around the parts. So to define that geometry, you define materials. So you define like moments of inertia and things like that. You define coordinates, and you define how your parts interact. So for example, we should have a joint here. So of course this looks highly complicated, but this basically just is describing your CAD assembly in a language that the simulator can understand. So I was trying to figure out how to go from OnShape to that, and I think previously in this video we hit a wall where like basically we were using there's like I think OnShape to robot GitHub. There's this repo here, OnShape to robot, which is very popular. But when you running through their example, we were hitting up a wall because we needed an OnShape API, I think. Let's see what they say. Anyways, my whole point here was like, if you need an OnShape API, you can just go to, and this is where I found these, but you can just go to, let's try to find a website. And you don't need to ask for permission or anything. It's like self-serve. It's here. Dev portal OnShape, this website, and then you get straight to this documentation. You go to API keys. You can generate an API key. And so that works. And so this repo, OnShape to robot, it's really good to go from OnShape to the URDF file to robot, right? Except, that will be enough if we're using Pybullet. But for one reason or another, we've decided to use MuJoCo. And MuJoCo actually doesn't take URDFs, but it takes something similar. It takes MJCFs. I have no idea what that means. MJ is probably MuJoCo, CF. I don't know, but it looks like this, right? So it's like similar. It's like an XML file, and it does the same thing. It defines your body, your meshes, and your joints, and I guess some sensors, which actually it's super relevant for the observation space down the road. I haven't gone too deep into that, but anyway, so this library will take you from OnShape to URDF, but it cannot do MJCF if you want to use MuJoCo. So I want to use MuJoCo, right? And so there were some hacky ways to go from URDF to MJCF, but none of them were working for me. And then all the tools that I could find for OnShape to URDF, they all have very specific conventions on like what should you name your joints, your assembly structure, and stuff like that, and how you should make your mates, and what those mates should be named. And I end up going with the K scale one, which of course it's run by a friend of mine, but it's basically here, right? So if you go to docs.kscale.dev, and they have this OnShape to URDF converter, it's pretty straightforward. Now these docs are a little raw, but what's cool about these is that with a single CLI command, you don't just go from OnShape to URDF, it also generates the MJCF. Kscale runs on MuJoCo, pretty sure. So that's cool. Yeah, if you end up using that, I like highly recommend going to their Discord. We had a conversation about this last night. Basically, you just need to name. No, you don't have to name the mates a certain way, but you need to not use connector mates. I don't know. I haven't exported the full robot onto this yet. What I've did, I'll show you, was I built like a very crappy example of like basically some very minimum geometry called MuJoCo experiment. Very minimum geometry with 2 parts, 1 mate, just to play with it. By the way, the other thing with Kate, well, actually, let me just show you. Of course, it takes forever to run. See, OnShape never works when you're recording your screen. Let's see. Okay, let's see what I can run faster, MuJoCo or OnShape. Let's find my terminal. I don't need any of these. Experiment 2, experiment 1, SB3. No. Okay, RL learn. MuJoCo OnShape. LS. And then I'm gonna just show you what I have. URDF. No. MJCF 2M. By the way, this is all on GitHub. You can see it. It's on the repo. Right. So I made this very simple part here. It's like, okay, it's flying right now because my origin is off. So the starting position is basically this going through the room. I think through the floor. And so it takes us as a collision, so it bounces off and then it starts spinning. But anyways, you can see here it's a block, and then I have this little arm that can rotate basically. And you can see it doesn't rotate all the way because I've set a minimum and a maximum angle. But anyways, this is basically it. Yeah. And so yeah, it works pretty well, right? So it's kind of like straightforward. I was trying to show you what the OnShape file looks like. It's not loading. It's pretty simple, right? It's exactly what you see here. This is an assembly with these 2 parts, a mate, a revolve mate, and the only thing it's like Kscale actually wants you to find a minimum and maximum angle. And I was chatting with them over Discord. It seems like it's spotty if you set a negative minimum angle. It doesn't like it, but I don't know. That could just be a bug. And all the code is open source anyway, so you can always just change it yourself. But yeah, that's where we are. I think it's a good spot to end the video. And this is what we have for next time. Install IMU, import robot to MuJoCo. Yes, I'm gonna add here our learnings here. So improve RL training pipeline, right? So 2 things. Infinite time run, no constraint on time steps. By the way, on this point, I think, I've been using TensorBoard by default just because that's what I know. I think there might be better alternatives. Basically, what I'm looking for is something that, I don't want to keep looking at the learning curve all the time. I just want to get an alert to be like, oh, the min reward function has crossed this threshold. Like, come take a look. Maybe get a text message. I imagine this has to exist somewhere. TensorBoard doesn't have this functionality, but you know, it's kind of like a simple idea. So somewhere out there they might have it. If not, maybe we'll go to a side quest and build this. But so that, and also like save model on every eval callback. That's also important. I guess I'll add one here, rerun experiment 2 with different algos. So yeah, so I kind of like really want to be able to train the bipedal walker without joint speeds, again, because that's what we have. And if that's critical, we might have to figure out a way to derive joint speeds, but I just don't think that's gonna be clean. So we can try, but it won't be clean. But on the flip side, like on the bright side, it's really good to see experiment 1 perform okay without the contact flags, because that means, you know, probably don't need to add contact sensors on the feet. So that's nice. I'm gonna add here PPO and TD3. And more time steps. Yeah, that is it.